we've got three really exciting talks by experts in their field over the next 3 weeks, and I hope you'll find them interesting and thought-provoking. So just to quickly introduce myself, I'm Robert Dunn. I'm part of the Future Leaders Innovation Group, and I work as a clinical scientist in cancer genetics. But the person that you really want to hear about today is our presenter, Lewis Couchman. Lewis has a master's specialising in analytical toxicology. He works at King's College Hospital in the departments of clinical biochemistry and toxicology. He's involved with research and analytical method development and validation using high-performance liquid chromatography and mass spectrometry for a range of toxicology and biochemistry-related analytes. His talk today is titled Comprehensive Insulin Analysis Using Mass Spectrometric Immunoassay, Applications and Future Potential. So, as I said before, there'll be time for questions at the end of Lewis's talk. So with that, I will hand over to you, Lewis, as presenter, and there we go. Over to you, Lewis.
Thank you very much, Rob. I hope you can all hear me. It's an absolute pleasure to be asked to give the first of these summer series of webinars, and I really hope that we'll have to
line muted
find of interest. It's some work that we've been carrying out in collaboration with one of our instrument manufacturers, Thermo Scientific, for a couple of years now, and we think what we have actually is a really useful clinical tool for the analysis of insulins, and insulins in the plural there is quite important, as you'll see. And what we're using is a technique that's relatively new, particularly for clinical analysis, which is mass spectrometric immunoassay. So I'll talk you through what that actually involves and share with you some of the data that we've managed to gather so far. I'm just trying to work out how I progress these slides. Here we are. Okay. And just to reaffirm here, the actual title is Comprehensive Insulin Analysis, as you'll see, and we're collecting data using really high-resolution mass spectrometry, and that's really what makes the assay as comprehensive as you'll see that it is, and gives us the ability to look back over the data in retrospect to really get a good feel for what's happening with regard to insulin biochemistry. So just firstly to introduce you to the concept of mass spectrometric immunoassay, which is given this abbreviation which we pronounce as MSIA. It's actually not especially new. It was first described back in the mid-1990s, but what it actually involves is a full workflow. It's not just a technique, which some people do consider it, but it's actually the entire workflow. So we go through from the sample preparation itself, which is key to the whole process, but also the MSIA as a workflow includes the data capture, the data analysis, and the data processing, which, as you'll see with high-resolution mass spectrometry, is actually critical to the whole process. But in a nutshell, what we have with MSIA is the combination of the advantages and benefits of immunoassay, which we use for the upfront sample preparation, sample enrichment, and then the detection capabilities of the mass spectrometry system. So perhaps the simplest way to describe MSIA is if you consider your classical ELISA type approach, all we're doing is swapping out the detection antibody for a mass spectrometer. So here you can see a picture of a typical ELISA process. Two antibody-based systems, so you have an antibody which is used to capture your target analyte, and then you have a secondary antibody which is labelled. That's the one that we replace, and in this case we're replacing it with a mass spectrometer, and actually we're replacing it in this case for the insulin analysis with a high-resolution mass spectrometer, and that's given us some really rich data, as you'll see. So if we just take a step back and we consider the use of LC-MS in clinical laboratories, really, for the analysis of peptides and proteins, I think there's still this opinion, and in some ways it is a correct opinion, that proteomics is really still confined to the R&D laboratories. So there's lots of work still ongoing with regards to proteomic mass spectrometry for biomarker discovery. And yet this is despite the fact that actually we're interested clinically in a number of important analytes that themselves are proteins or peptides. Insulin is one, but there are many others, including, for example, PTH, and many others. Perhaps the reason why LC-MS for protein analysis hasn't yet reached the high throughput routine clinical laboratory is due to some of the analytical problems that exist. These are listed here. Sample preparation is one, but as you'll see, MSIA is going at least some way to overcoming that. The sample preparation, of course, is especially difficult and is relevant to proteins which are at very low concentration, and insulin is one of those. Proteins, obviously, they're larger than the small molecules, things like vitamin D and other steroid hormones, so we are in some cases limited by the actual mass range of the instruments that we're using. And you can do things like digest your protein to give peptides to overcome some of these problems, but that has its own inherent issues. Chromatography is something to consider. The behavior of small molecules is arguably more predictable on some chromatographic columns, so there are chromatography considerations that we also have. And we also have to, of course, consider throughput, turnaround time, and the cost of the analytical process. So all of those things really do mean that proteomic work is going to be slow in terms of its uptake in routine clinical laboratories, but we are overcoming some of those things, and the MSIA workflow is perhaps one way to overcome some of those problems. The concept of using antibodies to enrich is not especially new. It's been around for some time. This was an editorial from ClinChem back in 2012. And really what we're using immunoaffinities for with the insulin assay here is to enrich the target analytes and the target protein as much as we possibly can, so that we can get down to the very low concentrations that we need for the insulin analysis. It's not unheard of that you can use antibodies to enrich your target protein concentration by as much as 1,000-fold, and that means that we can use the mass spec to detect these low concentration proteins. So this is how the actual workflow looks. This is a slide which is courtesy of one of our collaborators with Thermo Scientific. And the way we go about the immunocapture here is to use a mobilized antibody. It's mobilized onto these pipette tips. So we have pipette tips which have a fixed microcolumn in the end, and in this case we bind here an anti-insulin antibody. The sample preparation process is fairly straightforward. I'll show you in the next slide or so, but we pass the sample back and forth through these pipette tips, and that is all we need to carry out the enrichment. What we can then do is we can wash the tips to get rid of anything which is non-specifically bound, and we can elute the analytes which are captured and analyze them straight away by LC-MS. And of course what we also get here is the high value data content, so the data that we get from the high resolution mass spectrometry is really very rich, and I'll show you how we go about processing that data and reviewing the workflow. This is a fully quantitative workflow as well, as you'll see, so we do get full quantitative data out of the whole process. So the insulin workflow itself, I'll give you a very brief background to insulin analysis. I'm sure it's not needed for many of you, but we know, of course, that disorders of insulin synthesis, insulin activity, and insulin sensitivity are a big worldwide health concern. We have obviously diabetes, both insulin dependent and non-insulin dependent, and also gestational and pre-diabetes are perhaps even harder to sort of get a grip of and understand, and to actually understand what impact they have on healthcare. But in America especially, of course, this is a large problem. And statistics from a couple of years ago, I think now, from Diabetes UK suggest it actually affects quite a large proportion of the population in England. The other interest in insulin, and this is perhaps more where my background comes into coming about developing this assay, was from a forensic or toxicology point of view, where insulin is still used in cases of homicide. And also it's interesting in the field of sports doping. So we're actually working in collaboration with the Drug Control Centre over at King's College London, who obviously do the Olympic testing, and so they're very interested in adopting this methodology perhaps for the 2016 Olympics. We'll see. The problem, particularly from the forensics field, is that the immunoassays that you can use for insulin analysis are flawed because they cross-react, often to an unknown extent, with all of the different exogenous insulins that are available. So I'll show you some of the structures in just a couple of slides' time, but there are a number of these that are now available, and they primarily have minor structural modifications that are designed to adjust the pharmacokinetics of these drugs, so you end up with less frequent injection. But ultimately what that means is we can use the mass spectrometry to identify and pull out the different minor structural modifications that you can't necessarily do for just using immunoassay alone. Fortunately, with the immunoassay, you can use the C-peptide. So insulin, as you'll see, is produced as proinsulin. It's then cleaved into the insulin and the C-peptide. And so the use of the C-peptide Again, also currently carried out using an immunoassay, but is useful to help identify exogenous insulin administration, because you can use the insulin to see peptide ratio, seeing that the exogenous insulins that are available don't have the C-peptide. So use of that ratio is sometimes diagnostic for evidence of exogenous insulin administration. The other reason why insulin analysis by mass spectrometry may go on to be very useful is that there is immunoassay to immunoassay variability in terms of the results that are produced, which may well be due to cross-reactivity with other insulin analogues, but also other variant forms of insulin and proinsulin perhaps itself. There is work ongoing by the American Diabetes Association to look at the standardization of insulin assays, and they've stated in this paper from quite a while back, actually, 1996, there's still work ongoing though, that there is a need to recalibrate insulin assays, and the best thing to do is have some sort of reference method using a mass spectrometry-based approach. So that's hopefully what we're going to work towards. So this slide then shows you how we actually go about the insulin assay. So the first thing we do here is we take our MSIA darts, that's the actual pipette, and we just condition those with a bit of PBS buffer. So we just pass some PBS buffer back and forth through the tips. The next thing we do is we take our sample. We currently use 0.5 ml of serum, which is quite high, but we just see we've got quite good sensitivity, so we may well be able to reduce that in the future. And we add to that internal standard, and fortunately we have available to us a commercially available isotopically labelled insulin. So we dilute the insulin with this internal standard. We use a surfactant buffer which helps with any protein binding which may occur. And we do this all in 96 well plate format. You can see the picture on the right here. This is a small robot that we do have in the lab that does up to 12 samples at a time, but we can also scale this up to do 96 samples at a time. We then go through and do the immunocapture. So this is, we pass the sample, the diluted sample and the internal standard, go back and forth through the pipette tips 500 times. That takes around half an hour or so you can do 96 samples within about half an hour. We do a couple of wash steps with PBS buffer again, so fresh portions of PBS buffer. And then finally we elute everything that's captured onto the antibody with a mixture of some organic solvents, so some acetonitrile and a tiny bit of TFA. Trifluoroacetic acid. What we also do at this time is we add in quite a high concentration of ACTH. This is added as a scavenger peptide. So peptides and proteins, when it comes to the analysis of these, are quite tricky in that they have a tendency to stick to glassware and plasticware. So we try and reduce that as far as possible, and we take a number of steps. So we purposely use low bind plasticware. We add this ACTH, which is, we hope, a stickier peptide than the insulins that are captured, and so this high concentration of ACTH will serve to mop up any active sites on the plasticware or glassware that we're using. Once we've got our extracts, we just dilute those out with deionized water. That gives us better chromatographic peak shape, because the organic solvent in the elution buffer would serve to distort the chromatography that we have, so we just have to dilute that out slightly. And then we inject that directly onto our LC-MS system. And as I say, with this assay, what we're using is high resolution mass spectrometry, but you can also use this assay in conjunction with triple quadrupole instruments, so in a tandem mass spec approach. But for this, we're just using a full scan data acquisition at the highest resolution setting of the instrument that we're using. So just to show you some of the structures that we have, this is the proinsulin structure itself. So you can see the A and B chain of insulin here. So we have two A and B chain of insulin connected by 3 disulfide bridges shown here. And then the C-peptide, this is the bit that's cleaved, and so the whole thing is proinsulin. The C-peptide cleaves off and it leaves us with insulin itself. If you look in the BNF, again, this is a fairly old slide, so this is from a couple of years ago, but I don't think there's been too many new ones since. The important point here is that there's a number of analogues that exist. And also detailed here, you can see some of the structural modifications that exist. I'll show you the actual structures of some of them in a second. But they're all modified, as I say, to affect or alter in some way the duration of action and the pharmacokinetics of these compounds. So here's insulin itself, just the A and the B chain now with the C-peptide cleaved off. And to show you some of the analogues on how similar they actually are and why we have issues with immunoassays for insulin. The first one to point out is Humalog. which you can see is very, very similar indeed, actually, and we'll come back to this because this analog also poses problems for us with mass spectrometry. The only difference between human log and human insulin is that the very C-terminus of the beta chain here, and these two amino acids are just switched in terms of the order that they appear in the sequence. So the reason this is a problem for mass spectrometry, and I say we'll come back to this later because we've also found a way to overcome this issue, human log is completely the same mass and mass to charge as insulin itself. So we do rely on a secondary method to separate these two compounds. So we'll come back to that one just a bit later. Other analogues, things like the Nova Rapid, we've got an actual amino acid change in the sequence here, again towards the C-terminus of the B chain. That obviously infers a mass to charge difference, and we can use the mass to charge difference to distinguish this one from the human insulin. I should say also that the antibody that's on the MSIA pipette is directed towards a conserved region for all of these analogues, just around here, about 2/3 of the way along the beta chain. So when we do that immunocapture, even if there's multiple analogues present in the same sample, we can pull them all out from the same sample. And so far we've found plenty of capacity on the tip, even in the presence of multiple analogues. Just to show you a couple more, this is the lantus. We've got two additional amino acids on the B chain and a change on the A chain in this case. Lantus itself is an interesting one because what we actually see is when patients are given lantus, these two arginines are actually cleaved from the sequence, and so we're reliant then on the mass difference which is inferred by the A chain substitution to differentiate lantus and lantus metabolites from insulin itself. Apedra, again, another one with point changes. Porcine insulin we can differentiate, and the bovine insulin we can also differentiate. And even the two newer ones, which have got these fatty acid side chains, so the really long release ones, again, they give us quite different mass to charge ratios because of the presence of this fatty acid side chain. They also give us quite different chromatographic behaviour, so we can quite easily distinguish these two from insulin itself. So I mentioned right at the beginning that MSIA is a workflow that includes not just the sample preparation process that I've described, but also the data capture and data analysis. And key to the whole process for the insulins and for the high resolution mass spectrometry is this software which comes as part of the workflow, which is called Pinpoint. And this is just a couple of screenshots from the software here. So what we do is we can go online, and there's online resources now for protein mass to charge, mass spectrometry based experiments, so we can look up the amino acid sequences of each of these compounds. All we then do is type these into the Pinpoint software. So you can see for insulin here we type in the sequence. We can also include any positions where there are disulfide bonds, because obviously that will affect the mass to charge ratio of those particular amino acids. We can add in additional air in the C-terminus because it's a two-chain protein in this case, but we can also theoretically at least type in the masses or the expected mass to charge ratios and amino acid sequences that we'd see based on literature searching, for example, of insulin metabolites, so endogenous insulin metabolites. And the DESB30 insulin we can see here we're going to come back to later, but it's the cleavage of this very end threonine from the beta chain. Of course, we can also do the same for all of the analogues and also metabolites of these analogues. We can dial up the sequence for our internal standard, and we can modify the amino acids that are modified with regards to nitrogen 15 labelling. If you look in the literature, there are some very rare variants of insulin which again result in single amino acid changes, so we can dial up the sequences for those variants individually as well. And once we've got this sort of database, if you will, we can just use it to retrospectively interrogate our data, because if you remember, all the data we're collecting is just full scan data, so we're not pre-selecting any particular mass to charge data. Once you've got your sequence, the software will predict for you the mass to charge, the mass spectra, if you will, that you'll see for the insulins that you're looking at. So if you just look at insulin here, so endogenous human insulin, we've got our amino acid sequence here with all of the disulfides correctly placed. The software then predicts for us all of the different mass to charges that we'll see. And the way that proteins charge in mass spectrometry means that we actually get multiple charge states, because remember, we're looking for mass to charge, not just the mass. And so for insulin, you'll see a +4, a +5, and a +6 charge state. So you can see here, this is the +4, +5, and +6 charge states. And for each of those, you'll see isotopes within each because of naturally occurring, for example, carbon-13 isotopes. So effectively what you have from the software is a fingerprint such as shown here on the right. So this is the fingerprint of the +5 charge state for endogenous insulin. And effectively all we then do is use this fingerprint to try and filter our chromatogram and see if we can see the insulins in the sample. So if we carry out some experiments, this is a chromatographic peak now, so we've carried out our enrichment, we run it through our LC column, we see a chromatographic peak, and what you can see under this peak is 18 different extracted ion chromatograms which correspond to the top 6 isotopes from each of the top 3 most abundant charge states for the humanin, which is a recombinant human insulin. And of course they coalute on the chromatographic column. What we then can do is use the software to match what we're observing experimentally to what the software has predicted. So we get a theoretical versus observed isotopic distribution, and the software will give you a score for this. So obviously the closer that score is to 100%, the more certain we can be that we're looking at the correct insulin in the sample. And of course, alongside that, we've also got our retention time data for our calibration standards and QC material. Just some further data, this shows you some of the other analogues that are quite easy to detect using the workflow. So we have the insulin aspart. We also can pick up proinsulin, which is quite interesting, and again, that will offer us some research in the future. The glargine here, I put that in brackets because, as I mentioned, for patients taking glargine, we very rarely see glargine itself. We primarily see metabolites of glargine. And you can also see here detamere. So this is one of the really long-acting ones with the fatty acid side chain, and you can see the retention time here is much longer at 16 minutes compared to 8 or 9 minutes for the other 3. So I mentioned right at the beginning the most tricky analogue to look at with regards to mass spectrometry was the human log, which is, as I said, completely isobaric to human insulin itself. Fortunately, despite the fact that these are actually so similar, we can differentiate these two because they do just about separate on a chromatography column. It means your LC time is just about 15 minutes, but we also have a capability of doing a 2-channel LC, so we can speed this up to maintain our throughput if we need. So we can distinguish these two compounds using the LC, so we've got the retention time data that we rely on, because the fingerprints, both of these compounds, given that they're isobaric, is also very, very similar. You can use triple quadrupole mass spectrometers to differentiate these two compounds also. So if you use MS-MS or tandem MS, because of the order of that very end B chain and the way that proteins fragment in a mass spectrometer, you can actually get some unique, small but unique product ions. The disadvantage of that, and it's particularly relevant in forensic work, one of the things that we like to do for forensic cases is look at ion ratio or product ion ratio as an extra confirmatory criterion for suggesting that we're looking at the right compound. But because you only see one unique product ion for the human log versus humalin, we don't get that qualitative data. With this approach where we use the LC to separate the two compounds, we actually get the full fingerprint underneath each of these two peaks. So we actually get better qualitative data, and that's, I think, more important for forensic work. That said, with the mass spectrometer that we're using, we can actually do both of these things at the same time. So we can use them, we can collect full scan data, but we're doing this on a hybrid Orbitrap, so Q-exactive instrument, which means that we can do full scan MS, but we can also do some MS-MS. And actually, when you do MS-MS in this, what you see, here's the same chromatogram, but filtered using the pinpoint software. We see the theoretical isotope distributions for each of the two peaks. So this is for the peak on the left, this one for the peak on the right, and they both give us very good scores. If you look at the MS-MS spectra underneath each of these two peaks, so in cell E here you see the MS-MS spectra for the left-hand side of these two peaks, and in cell F this is the MS-MS spectra for underneath this peak. Here and here are the two unique product ions for the humalin and the humalog, and if we filter these data just for those specific product ions, again we get two quite nice clear peaks, but we've still got the full scan data that we can go back to and look at and give the product ion, the theoretical isotope distribution match as well. So we get really rich data from our high resolution instrument. I mentioned that the assay is fully quantitative, and this just shows you that here. So we can, as you would with any other assay, prepare calibration standards. We can go to the WHO and buy reference material for insulin. We're well covering the range that we would expect to see clinically for a fasting insulin normal range. We can go down to 1 million international unit per litre, or perhaps below that if we need. We can spike up IQC material, and this on the table on the right here just shows you that we get actually very good precision and accuracy at 10 and 25 million international units per litre for calibration, for QC material that we spiked ourselves in the laboratory. Fortunately, you can also buy insulin-depleted serum and use that to prepare your calibration standards. So you've got a nice matrix-matched calibration material for all of your samples. So that's where we are with the assay. And just to finish, a couple of quick applications, some work that we've done. It's preliminary work really, but I think has a significant future applications. The first of which is that Kings and Guys are involved in islet cell transplantation or whole pancreas transplantations for patients with diabetes. And of course this is a problem if you're testing production of insulin post-transplantation when a patient has previously been on exogenous insulin, because you'd like to be able to see the insulin production from either from the islet cells that have been transplanted or from the transplanted pancreas, but of course you can't necessarily do that in the background of remaining insulin that's been given. Just to show you here, this is very preliminary work, but we had a patient who was given, of course, it was the awkward, the Lispro, the Humalog one, so the isobaric insulin, and the top chromatogram here you can see the insulin that's been prescribed to the patient pre-transplant and post-transplant. You can just about see here a shoulder coming up. This is the successful islet cells producing insulin, and here we have the background of the Lispro that was prescribed to the patient. So this is very exciting, and I think it could be a really useful tool, because currently they rely on C-peptide immunoassay is really the only indication that they're getting insulin production from the transplanted either pancreas or islet cells. The other thing that's potentially interesting and useful, I would say, if we collect all of this data using FullScan, we have the ability to go back over it in retrospect, and we can look at things, for example, the DESB30 insulin. So in cases, for example, of insulinoma or proinsulinomas, what you tend to find, although these are rare, and this is an example from someone with a confirmed proinsulinoma, so we had a huge concentration of proinsulin in the sample, which you can see here, but we also observed at relatively high concentrations in comparison to normal patients, even those with high insulins, we could detect the DESB30 insulin, and actually we've got quite nice representation of the isotopic distribution that gave us a good score with the theoretical isotope distribution from the software, suggesting that DESB30 insulin was present. So it may well be that DESB30 insulin could be a new marker if we can test for it specifically, for example, for insulinomas or insulin-secreting tumours. So again, work ongoing, but we think it's a useful future application for the technology, and it shows the ability and the value of being able to go back over the data in retrospect. So that's where we are with the insulin. Just to conclude and perhaps think forward, the MESA workflow I think is actually a really useful tool. The affinity purification means that we can get down to very low concentrations, so for insulin it's very useful. Certainly it's fair to say that for some proteins and peptides you don't need to carry out such enrichment because the concentrations are much, much higher, but for some of these certainly low but perhaps even medium abundance proteins and peptides, many of which are proteins that we measure routinely in clinical samples on a daily basis, it could be a very useful tool. In this case, and in particular in conjunction with the Curative Active, so the high resolution mass spectrometry that we're using, it's really good for the insulin. It gives us really rich data, and particularly for forensic cases of forensic work, I think that's very important. There are methods out there, actually, interestingly, that measure insulins after having separated the alpha and beta chains, the A and the B chains, because you can get a bit more sensitivity because the peptides that you're actually looking at then are smaller. However, we think that that's perhaps not the best way to go, because we saw earlier on that there are metabolites or there are other exogenous forms of insulin which contain A-chain modifications, things like the bovine insulin, things like the glargine metabolites. So retaining that A-chain is actually quite important and gives us a wider scope for things that we can detect. The assay itself is very straightforward. There's no pre-tuning of analytes. All we have to do is know the amino acid sequence that we're looking for, and we can then process all of the data in retrospect, even months or years down the line. And as I've shown for the human log, this concept of getting really rich qualitative data and the use of isotope ratios is very important for us. So really that's all I have. If anyone has any comments, questions, if anyone would like to come over to King's and see the assay running, then please let me know. But I'll take any questions now. Thank you very much.
Okay, many thanks for an interesting talk, Lewis. So if anyone has any questions, you should see on the right-hand side of your screen a button saying Raise Hand. If you could click on that, and then I'll be able to unmute you one by one, so you can ask Lewis your question. When I unmute you, if you could just introduce yourself briefly as well. In the meantime, Lewis, maybe I could just ask a quick question. You said that insulin analysis is being used in forensic cases. Just wondered would it be complicated if the person was diabetic and was obviously on insulin themselves? Would you be able to sort of differentiate between that at all?
Yeah, that's a good question. I mean, all we have here is a tool to measure them. If we're asked whether there's an overdose or something to someone who's actually already prescribed it, that's a whole different question, and one for the lawyers to argue out more than one for us. But it's more useful perhaps in cases if someone who isn't prescribed insulin is inadvertently given insulin or mistakenly takes someone else's insulin, for example. Then we can come in and we can, if the normal range for someone for insulin, exogenous insulin is 0, then we have a really good assay for that. So yeah.
Excellent. Okay, thanks. Okay. There's a question from the St Thomas's Hub, so if I'm going to unmute you, if you could just introduce yourself and then fire away with your question to Lewis.
Hi, I'm Wasi from Consultant Biochemistry at Bedford Hospital. As you know, there is recently in America, they started to have and inhalers. Presumably you can pick this up equally if you have the right sample.
I'm sorry, I missed the middle part of your question there. Sorry.
I'm saying that in America they started prescribing insulin inhalers and patches.
Yeah.
And presumably the same application, you could pick this up with your analysis?
Yeah, absolutely. I mean, I presume all of the
amino acid sequence will be very different in inhalers and the patches as well.
The concentrations may well be lower, but I say we can modify this method to become more sensitive if we need. One of the beauties of the whole MESA workflow is that we need to increase the sensitivity, provided we've got capacity with the antibody on those darts, which we think we have. We can just keep increasing the sample volume as we need, provided we obviously can get the samples from the patients. But my guess is that for these patches or inhalers to be valid to be prescribed, the concentration should be fairly similar to what we're seeing with injections. So it should be no issue. But it would be interesting to perhaps test if we can get some patients who are taking them via these means. Then by all means we can look and see what we can detect. It might be quite interesting to do.
Okay, thank you.
Thank you. If you could just click the lower hand unless you've got another question from Bedford, thank you. Okay, so we've got a question from Dr. Misra. Dr. Misra, have you got a question for Lewis?
No, I haven't got any question.
Okay, no problem. If you could just click the lower hand button, that'd be great, thanks. Okay, so we've got a question from the St Thomas's Hub.
Hi, thank you, Lewis. Dominic speaking. Got two questions here. The first one is what's next?
Yeah. There's a long list, Dominic. With regards to the insulin assay, I say there's a couple of things ongoing. Firstly, we're working with the guys over at KCL. They're very keen on this as a technique. They did do insulin analysis in the 2012 Olympics using a really horrendous, long-winded technique. So they're really keen on this as a technique. So we may well see this in the 2016 Olympics, which will be great. Prospectively going forward with insulin, we've got some work ongoing with the guys who are doing islet cell transplants, as I mentioned. And there's also a study ongoing looking at harvesting islet cells within a box which is transplanted into patients. So there's really interesting work going there. In terms of other applications, one of our colleagues at King's is doing some work looking at MSIA for hepcidin analysis. We're looking at IGF-1 analysis, although I'm not 100% convinced that we need to go down to the concentrations to justify using MSIA for IGF-1, but we should see it's a comparison study that we're having ongoing. We've done lots of work with PTH, which is very useful, and we've published a review on PTH, so please go and have a look and a search for that. Yeah, huge amounts ongoing. Any other ideas, then please come and see me and we can discuss, because of course what we can actually do is put any antibody to any target on these darts, and we can potentially build an assay for that. So if you have any assays that you're struggling.
The second question here was how much does darts cost to make, and is it difficult to make?
It's not particularly difficult to make. There's a couple of options for this, and it's something really, price-wise certainly, it's something to discuss with Thermo. I know they're not particularly cheap, and price in comparison to an insulin immunoassay for the insulin is it's not prohibitive, but it's not a cheap assay. It's going to be at least sort of £10 to £15 for the assay by mass spec, just for the consumables. Perhaps more than that even. But what you get, of course, is multiple assays in one, because we've got effectively an assay for each of the different analogues. In terms of options for doing the binding, you can either do it yourself in the lab, you can either buy an antibody and ship it over to Thermo and they'll bind it up for you. You can buy streptavidin darts now, so anything you can buy attenuate, you can make you can make a dart for effectively. So lots of options, and as I say, if you're interested, please contact me and I can put you in touch with the relevant people at Thermo that we've worked with for a couple of years now. So yeah.
Thank you, Lewis.
Okay, has anyone else got any questions for Lewis at all? Okay, well, thank you very much, Lewis. That's fantastic. So we've got our second webinar taking place in a week's time on the 9th of July, in which Caroline Ogilvie from the Genetics Department will be asking how much information do we want from prenatal genetic diagnosis. So if that's something you'd like to attend, then don't forget to register on the innovation page of the Viapath website, and you need to do that by 5 p.m. on the 8th of July. Okay, so thanks again, Lewis, and thank you for everyone who was listening as well.